Good evening, we're Team Deadcode here to present our project on automated dynamic detection of SQL injection attacks, specifically for Python web applications. We built a tool that developers can use to modify their application in place to automatically prevent all SQL injection attacks.
Our solution can be broken down into three parts. Firstly, we have the dynamic taint analysis of Python's native string class. We do this using trusted bit arrays of zeros and ones and inherit the native string class to build a safe string class for tracking trust. Secondly, we implement an automatic string replacement module that passes code and wraps all string constants in the code with safe string invocations. Finally, we do syntax-aware analysis of SQL queries constructed using the new safe string class. We break it into syntactic components and ensure that the important components are trusted.
We perform dynamic taint analysis on the strings by tracking the trust value of each character in a safe string. We do this by inheriting from the Python string class. Depending on the source of the string, we initialize a trusted or untrusted bit array. Lastly, we override the inbuilt string functions to modify trusted string to reflect any string modifications appropriately.
For the automatic string replacement, we had two main concerns. Firstly, the distinction between static and dynamic strings. For static strings, we perform source code modification by passing the code recursively and into its specific abstract syntax trees. We then extracted all string constants from the tree and wrapped them with safe string invocations. For dynamic strings to safe strings conversion, we basically used overriding of functions from the inherited stir class. Since some of them may be identified during runtime, we use forbidden fruit to do this replacement. There's an example showing how when you have unsafe string on the left side of an add operation, you actually are calling store.add and not safestring.add, which shows why this is important.
Our approach to detecting SQL queries was to parse and decompose the queries into its components using SQL parse. We then verified the trustworthiness of important syntactic components. Untrusted strings were to be limited to literals and white spaces. If our code detects that any other component is untrusted, it would raise an alert or an SQLI. We have two examples here in the slide, one with and one without an SQLI. The red portions in the string are untrusted. The example on the left has an SQLI since or, equal to, and dash dash, which are not literals, are untrusted. The example on the right, however, will not be flagged since the untrusted portion is limited to a literal. We achieve this by overriding the execute functions of some of the most popular SQL libraries in Python. When an SQLI is detected, an exception of the corresponding library's error type is thrown with an appropriate error message. This ensures that the programmer has to do nothing but just run the automatic string replacement module against their code. The rest is completely automated. Now we have a demo of our code in action. So you can see that we're running the parsing module against the file, which is main.py, and saving it into a new file called newmain.py. Once that's done, this bit just compares the old file and the new file. I'm going to pause a bit here just so you can see what's going on. There are a few import statements that are added, which basically imports our module, and all the string constants in the code are wrapped around with our safe string invocations. Now we're going to run the safe and the unsafe programs to see that an SQLI injection is possible in the unsafe scenario, and it's not possible with the safe scenario. That is when our module is imported. So this is the unsafe program main.py, and when you run it, an SQL injection has been successfully performed. And when we run the new main.py, which is the modified code, an SQL injection is detected by our module.
As was mentioned earlier, we did automation of all the strings. So this was different from our earlier approach of allowing the programmer to specify how they want to treat SQLI attacks. Firstly, to do this, we faced two challenges in that the Python web application app.route does not accept safe strings due to a strict equality check for string objects. And in order to overcome this problem, we overrode the low-level compile function and changed our safe string object back to a string object, since this was not going to be untrusted in our opinion. The next part, as was mentioned earlier, is the automating of this SQL injection attack check. And this we did by checking all popular Python database servers and essentially exploring the execute calls, execute and execute many, and overriding those by wrapping them with an SQLi check and thereby calling the appropriate assertion error for these databases.
We evaluated our code by running against payloads that have an SQLi and that don't to measure false positive and false negatives. The results for this experiment are as shown. As can be seen, we have some false positive, and these primarily stem from statements similar to the examples shown in the slide. We're not too worried about these cases since they aren't valid SQL statements. This is because the DB will check for its syntactic validity and raise errors. For the sake of completeness, we included a SQL validator to weed out some invalid queries. Since DBs have subtle differences in syntactic rules, it's not viable to check in a given query if a given query is syntactically valid across all SQL flavors.
Now we'll have a small walkthrough to the Lab 6 code, which will show us how our new safe string invocation will work. So this serves as a good example because it has many of the things that are usually used in web applications, such as app.route, which was mentioned as one of the complications, as well as multiple string queries and execute statements. We are now calling our automatic string replacement, which you can see has added some import statements, as well as wrapped a lot of these string invocations with safe string invocations. We do see that execute does not have an SQLi call, but that's because we have overridden it to have an inherent SQLi query check, as well as the fact that app.route, even though it has safe string, will not be causing errors as stated previously. We start by looking at a valid example, and we can see that it is working. So valid normal SQL statements are working as expected. However, when we put an SQLi statement, we can see that we are getting an internal server error. And when we look at the error that is being thrown by the code, we can see that here we are getting a SQLi 3 error saying that SQLi has been detected.
We've also run our program against two other web applications. The first one is just a simple SQLi example. So as you can see here that we are running the parser against the sample application, and the source code has been modified. After this, again, we will run the safe web application and see if it's actually able to detect SQLIs. The web application is now running on port 5000, and I will open it now. We're first trying a incorrect login and password, and the login fails. Secondly, we try a valid username and password, and the login is successful. And finally, we try to use an SQL injection in the username, and we see that there's an internal server error, and there is an error that is raised here which says there's an SQLi that's detected. So this is the second application. It follows a similar methodology where we just run it against our parser, and then we set up the web application. When we open it, we have 3 SQL injection exploits that are available, and all of them are detected. And you can also see that the SQLi is detected and an error is thrown. Similarly, the other 2 SQLis also work in a similar fashion, and SQLi light errors are thrown whenever there's an SQLi. And the final SQLi injection is also throwing an error as expected. I just tried to run another random exploit, only to realize that there is no SQLite error thrown. So now we will go on to our final presentation, our final demo, and Agnes will take over.
So what we have here is essentially a Python playground web application for anyone who wants to play with our library. Essentially, what it allows you to do is to mention a query format, as well as the user input you want to give to that query format, and kind of see how if it will detect the SQLi injection or not. The first query we've supplied is an SQLi, and it has been detected. The second one is not an SQLi; it's a valid query, so it's been given the green light. However, there's a third one that is an invalid SQL query, which can also be construed as a SQLi. However, because of its invalidity, it has been marked in yellow because of the fact that was mentioned earlier. So this web application will serve as a good playground for people to test out different queries and see how this library will work for their purposes. And that brings us to the end of our demo. Thank you so much for listening to us.